So in the previous videos, you've hopefully followed me through the derivation of the aircraft equations of motion. But we've derived them for a generic flight condition. So we can solve those equations for any moment in flight to tell us what the aircraft is actually doing. But there are a couple of special cases for which we're able to significantly reduce down the complexity of the aircraft equations of motion to give us a much more simple solution. And these two special cases are the steady state flight condition. So think like in a cruise, like rectilinear flight, straight line flight, right? Or in a steady turn at constant altitude, something like a symmetric pull up or push down, like a symmetric loop, for example, in a cruise climb or cruise descent. So if we consider one of those particular scenarios, we're going to have zero rates of change for our linear and angular velocities, right? So that's just going to significantly reduce down all of those derivatives that we have in our equations of motion. And the second special case is what's called perturbed flight conditions. So this is all to do with how the aircraft deviates from a steady flight condition. So if we have an initial condition which is known, a steady state condition, how does the aircraft respond to a very small change in configuration to that? So think like in a maneuver or during turbulence, for example. So we're going to go ahead now and take a closer look at both of these special cases of flight condition. So let's take a look at our steady state flight conditions then. So we just summarized these just now, but just to remind you, this covers cruise conditions, steady turns, symmetric pull-ups, push-downs, that kind of thing. And the assumption of a steady state conditions means that we have basically zero rates of change in our linear and angular velocities. So if our linear and angular velocities are constant, then our linear and angular accelerations are zero, which means that all of these components are zero. So the components of the linear velocity vector and the components of the angular velocity vector are all zero. So this means that we can quite heavily reduce down our aircraft equations of motion. So starting with the conservation of linear momentum equations, we can get rid of all of these terms here, which are the accelerations in the linear velocity vector. And then also in the conservation of angular momentum equations, we can get rid of the accelerations in the angular velocity vector, so p, q, and r dots. The kinematic equations, however, stay the same. So there is one further simplification we can make to those equations, in that if we consider a cruise flying in a straight line, constant altitude, wings level, we have an angular velocity of zero, right? So if we have an angular velocity of zero, all of these terms disappear here as well. All of these terms in here all disappear as well. So what we're left with is just this system over here. So that's for the very specific case of a cruise condition.